So we have studied about crystalline and amorphous. Let's understand the difference once again in a tabular fashion. So we talk about the crystalline. The examples are my diamond, quartz, sodium chloride, that is NaCl, common salt. We talk about the amorphous. The common examples are plastic, rubber, and the glass. The first difference was the crystalline have a regular 3D arrangement of particles due to which they have well-defined geometrical shape. For amorphous, they do not have regular arrangement and they do not have well-defined shape. Actually, this is shape. Correct? They have long range order. If you see this, if you just expand this, you will see the same order for a long distance, maybe thousands and lakhs of molecules. These guys the amorphous have short range order. In fact, there is no order in this picture. There is not. They have very sharp melting point in crystalline. We saw that you heat it at a given temperature X, it melts. They don't have sharp melting points. It melts over a period of temperature X degrees Celsius to Y degrees Celsius. It melts actually. It slowly melts. They have fixed and very high heat of fusion. Why high? Because they are all symmetrical, very strong. So they have high heat of fusion. And they have less. These guys have small heat of fusion, but they don't. These guys have fixed heat of fusion. They don't have fixed heat of fusion. Again, they are anisotropic. Why? Because the arrangement is fixed. If you go in this direction, if you go in this direction, it's all different. So they are anisotropic. Their physical property is different, right? For the same crystal, if you're observing from this direction or this direction, since there is no arrangement, you go in any direction, it's almost same. So they are isotropic. Their physical property doesn't change with respect to the direction. They are true solids. Crystallines are true solids, but they are pseudo solids. In fact, they are super cooled liquids. Correct. So this crystalline show two breaks in cooling curve. We have seen this cooling curve, and this has a smooth cooling curve. This crystalline is more stable, more sturdy. Amorphous is less stable. And when you cut with a sharp tool, this is something we didn't discuss, I think. When you cut with a sharp tool, this crystalline is split into two pieces. And this newly generated surface will also have plain and smooth surface. Correct? But with this amorphous, when you cut, you have this knife actually, this is knife. And with this knife, if you cut this amorphous solid, they will cut into two pieces, but the surface will be irregular surface. Please note, here will be plain and smooth surface, right? Here you will get irregular surface. See, crystalline and amorphous are the extreme case we discussed, right? But naturally we have seen that all the substances are not pure crystal or pure amorphous. We have something called polycrystalline, which is something in between crystalline and amorphous. Correct. So these are solids which composed of crystallites of varying size and orientation, but they are separated by fine grain boundaries. So you see, they are nothing but, I'll write here, solids composed of many crystallites of varying size and orientation separated by grain boundaries. You see, this is one pattern here, there is one pattern here, there is one pattern here, right? So there are different boundaries here. Therefore, there are many crystallites like that, but they are separated by boundaries. Correct? So if you see, almost all common metals, if you see, all common metals, they fall in this category, and some polymers also fall in this category. For example, sulfur. Sulfur occurs as polycrystals. It also occurs as single crystal. It also occurs as amorphous. So sulfur exists in all three forms. Correct. And the degree of crystallinity, as we told, has a huge influence on hardness, density, transparency, etc. So there are so many things actually, no? I mean, what I'm trying to say is nothing is pure. We have something called polycrystalline also. And this crystallinity is something which you can measure using X-ray diffraction, calorimetric, those kind of techniques, right? So single crystals are rare. Single crystals are like gems or silicons or diamonds, quartz. They are single crystals. But generally, metals you see, they are polycrystalline. If you see metals like iron, copper, gold, they are all actually polycrystalline. Correct? If you talk about crystal, then you have sodium chloride, zinc sulfate, all these things. What I'm trying to say is we have something called polycrystalline, which is also there. But we'll not discuss much about polycrystalline. Whatever is polycrystalline for this chapter at least, we'll assume they are crystalline itself. In this chapter, we'll assume iron, copper, gold are crystals. Why I introduced you this term is because in the previous slide, we told that something which melts, right, are crystals. But if you see, they also melts. Sorry, I told amorphous, but they also melt. So they share some properties of crystalline amorphous also. But for us, now let's talk about some of the examples of these solid states. And the crystalline, polycrystalline, and amorphous, and the uses of these solid states. We talk about the metals like iron, copper, and gold. They are polycrystalline. So these are my polycrystalline, right? My iron, copper, and gold. Correct. So we talk about sulfur and silicon. The sulfur exists in all three forms actually. So we'll talk about that. And if you talk about these sodium chloride, this is my sodium chloride. Or if you talk about, this is a naphthalene. And this is my zinc sulfide. Zinc sulfide. These are my, again, crystallines. Sodium crystal, NaCl, you know, is common salt. Naphthalene is used for aroma in bathrooms and cupboards. Zinc sulfide is used for cathode ray. In cathode ray, zinc sulfide. You see, they have crystal structures. We'll talk about these structure in details in the few slides. And the sulfur exists in all three forms. If you talk about silicon, it also exists in all three forms, and amorphous silicon. This is used for photovoltaic cell. And if you talk about crystalline silicon, it is used in semiconductor. So we'll talk about these crystalline silicon also in details. And if you talk about these plastic, rubber, and glass, they are my amorphous. Yeah, these are examples of my amorphous solids. This is my crystalline silicon. Actually, it's also used in semiconductor.